Happy Chapter 3 warm-up, everybody. Sketch f of x equals negative 3 times the quantity x plus 4 squared plus 12. Identify the zeros, the roots, and the x-intercepts. Okay, so this is this is a quadratic. It's a quadratic because it's degree 2, and it's a polynomial, right? You've studied polynomials in Algebra 1 and Algebra 2. You studied linear polynomials in Algebra 1, and this is a quadratic polynomial. And it's also in vertex form. So the vertex is where? Negative 412. Yeah. You know by transformations that you don't have to memorize that this is in vertex form. All you need to do is realize that it's in standard transformation form. So the parent function is x squared. It's a parabola that opens up. The negative is going to reflect it across the x-axis, which makes it open down. The 3 is a what? Vertical stretch by a factor of 3. And then, of course, it's left 4. Up 12, and that's how you know the vertex is at negative 412, because the vertex started at 0, 0. So if we're going to sketch this dude, we're going to come over here to negative 4, 12, and we're going to put the vertex. Okay? Now, I know it opens downwards, so I could draw it looking something like this. Oops. We want to draw it symmetrically, right? Because there's an axis of symmetry that runs right through here at x equals negative 4. That's the axis of symmetry. If you remember from Algebra 2, it folds right across that line. But I want to know where it crosses the x-axis. I want to know where that point is, and I want to know where that point is. Let's go ahead and find the y-intercept first, okay? The y-intercept. The y-intercept is the easier of the two to find, because all you have to do is plug in a 0 for x, f of 0. What are we going to plug in as 0? We get negative 3 times 4 squared is 16 plus 12, and that gives us negative 48 plus 12, which is what? Whoa, okay. Is my graph drawn to scale? I have my y-intercept in positive lane, don't I? So if I want to try and draw this at least somewhat accurately, I'm going to need to, oops, I got rid of my 6 over here. I need to change it a little bit. So I'm gonna do that. I want it to be somewhat accurate. So I'm going to draw it like this, and then here's the y-axis, and then it comes in and opens like this. There it is. So here is the y-intercept of 0, negative 36. Good morning. And now for the x-intercepts, I know now that my x-intercepts are both negative, aren't they? Yeah, so I need to find the x-intercepts. So how do we find the x-intercepts, which are also called the roots of the zeros? We don't plug in a 0 for x, we do what? We plug in a 0 for y, which is f of x. In other words, we set it equal to 0. You set the function equal to 0. So we're going to get negative 3 times x plus 4 squared plus 12, and we're going to set it equal to 0. Now, the reason the y-intercepts are easier because you're just plugging in and evaluating. Here you're setting it equal to 0, so you're having to do what? What's the word? Rhymes with volve? Solve. Trying to solve. Yeah. So we solve. If I solve this equation when it's equal to 0, I get my roots. I get my zeros. All right, so I'm going to go ahead and subtract the 12 first. We're trying to get at the x plus 4 squared. So I subtract the 12, and then I divide through by negative 3. What's negative 12 divided by negative 3? 4, and then I take the square root of both sides. And when I take the square root, I have to remember to do plus or minus the square root of 4, right? Now that's going to give you a fork. That's two equations. I get x plus 4 equals positive 2, or x plus 4 equals what? Negative 2. Yeah. And now when I solve that, I get x equals negative 2, or x equals negative 6. So this is negative 2, and this must be negative 6. These are called the roots. These are also called the zeros. These are the x-intercepts. And they're also the solutions to the equation f of x equals 0. They all mean the same thing. They all mean the same thing. All right, now what does the graph of this look like? This is called a parabola. 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 Got one bolus. I got another bolus. I got a pair of bolas. Yeah. All right, any questions on that? I'm going to take attendance while y'all devour that. Oh, there we go. All right. So that's a good segue into chapter 3. So let's go ahead and open chapter 3 up. Notes, chapter 3, polynomial functions. Nice. Okay. So is anyone showing it on Canvas? Yeah, try to refresh. Yeah. I activated it this morning, so it should be fresh. I didn't want to give you day old chapter 3. Ugh. The bread gets soft and everything. All right, let's take a look at polynomial. What? First of all, let's look at the word polynomial by itself. It's made up of two words, uh, polyno and meal, right? No, that's not how we break it down. Let's try it again. Po and linomial. No, no. How about poly and nomial? There we go. I think that's how we break it down. Of course, y'all know from y'all's roots that poly means what? Many, right? Polynomial, many. Guess what nomial means? Numbers, yeah. Literally, it translates as names. It could be numbers, but what it really means is terms, many terms. Okay, polynomial, many names, many numbers, many terms. And y'all remember what a term is, right? A term is separated. Let's write this right here. A term is separated by plus or minus. Okay, it's the difference between terms and factors. We've already talked about that this year, terms versus factors. So polynomial means many terms, and of course a function is something that has only one output per input, right? Passes the vertical line test. So these are going to be functions that have many terms. Now, you can have functions that have many terms and not be polynomials. So what really makes it a polynomial? Here's what makes it a polynomial. A polynomial function is written in the form f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus blah, 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 all the way down to a sub 2 x squared plus a sub 1 x plus a sub o, okay, where a sub n is not equal to 0. So what the heck does this look like? Well, first of all, we have these a subs in the front. These a subs, I'll just write this right here. These a sub i's, these are your coefficients. Okay? And then the I is the index that corresponds to the degree of that term. Okay? So a sub 2 would be the coefficient of the x squared term, the number in front of the x squared term. A sub 1 would be the coefficient of the x to the first term, which is called the linear term. Okay? A sub o would be the coefficient of the x to the 0 term, which is just 1. So a sub o is your constant. A sub o is your constant. A sub 1 is your linear coefficient. A sub 2 is your quadratic coefficient. So on and so forth. Okay? So your a sub i's are the numbers in front of the variables, and they correspond to the power or the degree. A sub n is the largest one associated with the largest degree. This one is called your leading coefficient. And it's associated with the largest power. And by power, I mean degree. Okay, so we're kind of dissecting, sorry, cutting it apart, looking at its parts. Your x's, of course, I don't think I need to go through the x's, but your x sub n's, your x squared, x, and whatever, those are your variables. So your x sub n's are your variables. All right. Your n is called your degree. It is your largest exponent.
So will your coefficient and degree always match up?
Well, the name of your coefficient, you can sit on the desk. Yeah, a sub n. So whatever number is in front of your largest degree, we're calling that the leading coefficient. If the degree is 3, then we call that term a sub 3. Okay, a sub 3. These are going to actually be numbers. Now, what makes this a polynomial is very, very important. Okay, here's probably the most important part of your polynomials. Your power n has to be an element of the whole numbers. The whole numbers, which is w. The whole numbers are this. It's 0, 1, 2, 3, dot, dot, dot. Your powers on your n's have to be whole numbers. They can't be integers. They can't be negative whole numbers. You can't have a negative exponent and call it a polynomial, okay? Because a negative number is not a whole number. You can have 0 because this a sub o is really times x to the 0, okay? So you can have a power of 0, but you can't have a negative exponent. That's what that means. Let's write that here. So no negative exponents. No negative exponents. If you ever see a negative exponent, you don't have a polynomial, okay? Now, it also can't be a fraction, okay? So you can't have fractional exponents either. No fractional exponents. Fractions show up as what? What's another way to write a fractional exponent? Yeah, square roots, okay? So if you ever see a function that has a square root or a cube root or any type of radical in it, let me put roots or radicals. If you see a function that has any type of radical in it, it's not going to be a polynomial, okay? If you see a denominator with a variable, it can't. That's the negative exponent. It's not going to be a polynomial. So no negative exponents. Let's write what that means. That means variable in the denominator. No, your polynomials are just going to be very, very simple numbers, like 5 and 7 and 13, okay? They're going to be nice whole numbers. Now, we just kind of dissected this up here. This is called the standard form of a polynomial function. It's written in descending order or decreasing order of degree or powers, okay? So we start with the largest exponent, and then we write it down in descending order of degree all the way down to our constant. Y'all seen standard form before. Y'all had that in algebra 2, the standard form of a parabola, okay? Here would be an example of a standard form of a parabola. It would be like 3x squared plus 4x minus 1, okay? The parabola that we saw in the warm-up was not in standard form. It was in vertex form. And I put it in vertex form because I wanted y'all to graph it, all right? Here's another example of standard form. Let's do 5x to the 7th plus 2x to the 5th minus 3x to the 4th plus 2x cubed minus 7x plus 1.
If there's no x to the 6, if you just put a 0 there?
Yeah, very good. I was going to talk about that. No, very good. You anticipated the question. This is written in standard form because it's written descending order degree. What would the degree or the power, what would the degree of this function be? 7. This is a degree 7 polynomial, okay? Up here, this is a degree 2 polynomial. Now, if there is no x to the 6th term, that means that its coefficient is what? 0. Yeah. So you don't have to have a representative of every power smaller than n, but n itself has to be the power. We call that a 7th degree polynomial, not an 8th degree polynomial. You can't say that the coefficient in front of the x to the 8th term is 0. It doesn't work. You take the largest non-zero term with this coefficient, and that becomes the power. So what would a sub n be? What would the leading coefficient be?
5.
5. This is your leading coefficient, and if you wanted to give it a name, it would equal a sub 7. A sub 7. Okay? The leading coefficient would be 5. What would be the cubic coefficient? Cubic means what? Cubed, right? To the 3rd power. So 2 is your cubic coefficient, and in this case, it corresponds to a sub 3. A sub 3. It's your cubic coefficient. What would be your linear coefficient?
A sub 1.
What would it actually be here?
A sub negative 7.
No, your linear coefficient is -7, and it corresponds to a sub 1. It always corresponds to a sub 1. Okay, the subscript on your a's corresponds to the powers on the variables. Does that make sense? That's why I used I there. I is for index. So your linear coefficient is -7. What would your quadratic coefficient be? If there's no x squared term, what's your quadratic coefficient? 0. Yeah, it'd be 0. Okay, so a sub 2 is 0. What is your constant?
1.
1. And that corresponds to a sub 0. Okay, your constant is a sub 0. The -3 in front of the fourth power, we call it the quartic coefficient. We go up from cubic to quartic. And guess what we call the ones in front of the fives? We go quartic, we go linear, we go constant, linear, quadratic, cubic, quartic, quintic. Very good. Quintic. Very good. And then after degree 5, we don't really say much anymore. We just say 6th degree polynomial, 7th degree polynomial. But it would be like hextant, and then heptant, and then octant. But we really don't do that. But quintic would be the highest we go. Very good. There's another example right there. 5, 4, 3, 2, 1. That one has the representative of everything. Okay. Let's come down here, and we're going to do example 1 now that we have an idea of what this all means. Identify each of the following as a polynomial P or not a polynomial N. Be sure to understand why. Okay. F of x equals 4x squared plus the natural log of 3 times x minus 1. Is this a polynomial or not a polynomial? What makes it a polynomial? Identify all your variables. Look at your variables and then look at their exponents. What's the exponent on x squared? I highlighted it. 2. Is 2 a whole number? Yes. Okay, so that passes. What is the exponent on the x? 1. A 1. Is that a whole number? Yes, that's good. Are there any other variables? No. So does it pass the polynomial test? It has to have whole numbers on every single variable. Yes. So this is it. No fractions, no radicals, right? No fractions, no radicals. So this one is a polynomial, and I'll just write it with a highlighter because that's what I meant to do. On purpose. P for on purpose. Purpose. All right. So that is a polynomial. Letter B. I got f of x equals 10x squared minus 11x cubed plus 3 to the x. Is this a polynomial? No. Is the first term a polynomial term? Yes. Is the second term a polynomial term? Yes. But the third term has what as its exponent? An x. Is that x always going to be a whole number? No. X can be anything. It could be a decimal, a fraction, a negative number. That's an exponential term. So this would be no. This is actually an exponential term.
So the e to the x will never be a polynomial?
Correct. E to the x is never a polynomial. So this is n. This is not a polynomial. The exponential term ruins it. Okay? Sorry, 3 to the x. It's a function, right? It definitely is a function. It passes the vertical line test. It's just not a polynomial. Okay, how about letter C?
No.
No, who's the culprit?
2/3 and negative
2/3. Okay, let's look at 2/3 first. This is a fraction. So it's really the same as x squared cube root of it, right? So it's a radical in disguise. So that's a no. We know it's a no based upon that. Now let's look at the -2. Is the -2 on a variable or on a number? It's on a number. Is that okay? Yeah, that's okay. Your coefficients can be any real number. Your coefficients can be any real number. It's the exponents that have to be whole numbers. So this term's okay. This is really just -1 over 81. That's what that's equal to, 1 over 9 squared. But the 2/3 is no bueno because it's on an x. Everyone see that? Okay, very good. Let's look at letter D. X times 2x squared minus 3x. Is this in standard form?
No.
No, it's not in standard form. We better put it in standard form to see if we can identify it, which means I have to do a little algebra first. Okay, that becomes 2x to the what? Cubed minus 3x to the squared. Now it's in standard form. Is it a polynomial?
Yeah.
Yes, it's a polynomial. What's the degree of the polynomial?
3.
3. It's degree 3 polynomial. What's the leading coefficient? What's a sub 3? 2. That's your cubic coefficient. It's your leading coefficient. It's called a sub 3 because it's associated with the x cubed term. Very good. What would a sub 2 be?
3. Or negative.
Negative 3. Good. That's what's associated with the square term. What would a sub 1 be? 0. What would a sub 0 be? 0. Good. There's no constant, a sub 0, and there's no linear term, so their coefficients are 0. Fun easy, right? Polynomials. They're the easiest, simplest functions to work with because their exponents are nice baby whole numbers. All right. Letter F. 4 over x squared minus 7x plus x squared. Polynomial, yes or no?
No.
Are you sure?
It is.
Are you sure it's no? Or are you sure it's yes? Or are you sure it's maybe?
I'm sure it's yes. Yes.
Do you see any negative exponents? No. Do you see any fractional exponents? No. Does that pass? Ah. I don't see any negative exponents, but do you see any negative exponents in disguise?
Yes.
Ay, caramba. That first term, that x squared, is not in the numerator, is it? It's in the denominator. That's the same as 4x to the what? Negative second. Oh, okay. So you can't have radicals and you also can't have variables in the denominator. This is a negative exponent. So guess what? No, it's not a polynomial. I'm 100% sure it's not a polynomial. It has polynomial terms, but they all have to be polynomial terms.
What happens if there's instead of it being a x squared on the denominator, x to the negative?
Oh, that would be close to a polynomial. Good question. If this were 4 over x to the negative second, that really would equal 4x squared, right? If you brought it to the top. But before it becomes 4x squared, it really becomes 4 over 1 over x squared. Yes, yes? And now notice what the domain is. Are we allowed to divide by 0? No, x can't be 0. So this brings up another important property of polynomials. Polynomials have domains, very good. They have domains of all real numbers. So even though it would simplify to 4x squared after that intermediate step of 4 over 1 over x squared, because the domain would not allow 0, it's the closest you can get to a polynomial without being a polynomial. It's an imposter, right? It's an imposter. That's a great question. I should probably add that to the notes for next year, following up on this question right here. I'm glad you did that. Okay, polynomials have domains of all real numbers. You find the domain before you simplify, right? We learned that on the last test, didn't we? Or we've been talking about that all year, actually. All right, let's look at letter E. F of x equals pi times x cubed plus 7x plus ex squared plus the natural log of 1. Polynomial, yes or no? Let's see where the x's are. I got x cubed, so 3 is a whole number. That looks good. I got x to the first. Gosh dang it, why can't I just write with the correct thing? I got x to the first, which is a polynomial, or a whole number, sorry. And I've got x to the second, which is also a whole number. And that passes, right? So check, check, check. Check, check, check. Now look at the coefficients. The coefficients can be any real number. Is pi a real number? Yeah. Is e a real number? Yes. And what is the natural log of 1? You all remember from the parent function?
0.
It's 0. The natural log of 1 is 0. So that term's not even there for real, right? If we simplify, a sub o is 0. Okay, cool. What would be the degree of this polynomial?
3.
Degree 3. We call that a cubic. Like a parabola is a quadratic, we call that a cubic polynomial. What is a sub 3? Pi. Good. What is a sub 2? Careful. It's not written in standard form, is it? They're written out of order. Yeah. A sub 2 is E. A sub 1, the linear coefficient, is what? 7. And then a sub o, the constant, is
0.
the natural log of 1, which is 0. Yeah, good. So we can call it the cubic coefficient. We can call it the quadratic coefficient. We can call it the linear coefficient. Or we can call it a sub 3, a sub 2, a sub 1. The subscript on each of those a's corresponds to the what of the x? The degree or the power. Yeah, the power. Either one. Degree or power. All right, moving on. Example F. 3 times the square root of x minus 7 cube root of x. Is that a function? Is it a function? Yeah, it's a function. But is it a polynomial function? No, I got radicals, right? They're both bad. They are both, this is the same as 3x to the 1/2 minus 7x to the 1/3. And we have fractional exponents on both of them. This is not a polynomial. So that is not a polynomial. Oh, this one over here, I didn't even write the P. P for polynomial. Okay? Not a polynomial. And then letter G.
No. No. Wait, no.
This kind of goes back to Peyton's question. X cubed divided by x would simplify to x squared, wouldn't it? And then here, if I brought the x to the negative second to the top, it becomes 2 times x squared, doesn't it?
Yeah.
And then over here, if I take the square root and square it, that just becomes x to the first, doesn't it? And then pi to the 0, that becomes 1. It simplifies to this, which is a polynomial. But is that the genetic makeup of the actual problem? No. This one, the actual problem, doesn't allow zeros in the denominator, nor does it allow negatives under the square root, does it? So the domain is not all real numbers. I'll get it. The domain is not all real numbers. So is it a polynomial or no?
No.
It is not a polynomial. This one is very, very close to a polynomial. This is an imposter. It's an imposter. You wouldn't see the graph anywhere to the left of 0 if you were to graph the original function, and you would have holes at 0. And maybe even a vertical asymptote at 0. Okay? So even though it simplifies to a polynomial, it doesn't make it a polynomial, right? If you see a person wearing a ghost sheet, does that mean they're a ghost? Just because they look like a ghost? No, because when you look at the DNA under the sheet, it's a human being, right? There's a human being under there. Unless there isn't. Whoa. Have you ever thought about that? Like you see a floating sheet and you're like, oh, that's just a ghost. But really, it might be a ghost wearing a sheet, right? When you see a sheet floating with eyeballs, was that what ghosts look like, or is that just what ghosts wear? Or I guess maybe that's maybe yeah. There's the sheet, right? Yeah. The ghost, it does look like a worm. The ghost itself would be wearing the sheet, right? So you can see it. But the sheet itself is not part of the ghost. The clothes don't make the man. Okay. I'm good at drawing ghosts. Yes, very good. I'm good. It looks like Pac-Man ghost. That's my reference for all ghosts. I tried to do one that was kind of on the move, like there's wind back here, like he's moving fast, you know.
Did everyone eat all your pickles?
What's that?
Did everyone eat all your pickles?
Yeah, the pickles were gone by second period.
Very sour.
Yeah. Were they? Yeah.
The second period.
Yeah, second period, they opened them up, man. They devoured them. They like the pickles. Okay, so we know now how to identify a polynomial from the equation. Yes? It can have negative exponents. It can have fractional exponents, which means it can have denominators with variables, and it can have radicals with variables, right? They have to be nice whole numbers, 0, 1, 2, 3, 4, 5, etc. Okay? Now, how do we identify it from the graph? Well, what do negative exponents translate to on graphs? They either translate to vertical asymptotes or holes, right? Or jumps. So are we allowed to have holes, jumps, or VAs on polynomials? No, let's look at it. So we can't have no jumps, no holes, no vertical asymptotes. Because that's what negative exponents and fractional exponents manifest as on graphs. Okay, so no jumps, holes, or VAs. They have to be then what? If they can't have any of those, they have to be what? Continuous. Okay, they must be continuous with a domain of what?
All real numbers.
Domain of all real numbers. Yeah. Okay. So let's look at this one. Example 2. Is this one a polynomial or not a polynomial? Not a polynomial. Who's the culprit?
Break
The,
and the whole.
the break and the hole, the jump and the hole. Yeah, they're both culprits. Not a polynomial. What about this one? It is smooth and continuous, and this implies that it goes on forever and ever. This one is a polynomial. Is it a quadratic?
No.
Does it look like a parabola? No, it looks partly like a parabola, but it's got too many wiggles, doesn't it? This one is actually going to be a degree, not 3, not cubic. It's actually going to be degree 4. Yeah, we'll learn why it's a degree 4 here coming up, but it's actually a degree 4. Okay. Let's look at this one here. It's got a corner, a sharp turn, and it's got a cusp. We call that a cusp. A cusp is when two sharp corners come together curving wise. You think this is a polynomial?
Yeah.
Well, what if I told you that x to the 2/3 looks like this? It's the same as the cube root of x squared. Would that be a polynomial if I just gave you that equation? No. Here's what the graph looks like. Oh, I don't want to put y equals over there. The graph of x to the 2/3 looks like this. It comes in like this, and it leaves like that, and you get a sharp turn. So sometimes when they're odd roots, they manifest as sharp turns. The radicals manifest as sharp turns. So there's another visual clue that it's not a polynomial. Can we have any discontinuities for to be a polynomial? No. Can we have any cusps for corners or sharp turns? No. So we can't have no corners, no cusps, no sharp turns. Even though this one's continuous and has the domain of all real numbers, it has a corner, cusp, or a sharp turn. That's no good. So this is n. No, it's not a polynomial. Not a polynomial. All right, let's look at this last dude here. Do you see any discontinuities? No. Do you see any cusps or corners or sharp turns? No. So guess what? These imply arrows on the end, so this would be a polynomial. Anyone want to try and guess what degree this one is? It would actually be degree 5. Yeah. Quintic. Degree 5 would be quintic. Okay. We've only seen 2 that were more than degree 2. The degree 4 over there on part B and the degree 5 on part D. You can probably already start coming up with some type of general rule for polynomials based upon their degree and their end behavior. Whether they come in from the bottom and leave out the top, or they come in the top and go out the top. What do you know about parabolas, which are degree 2, and this one, which is degree 4? They come down from the top, and then on the right-hand side, they go out the top, right? That's going to be a common characteristic of any even degree polynomial, whether it's degree 2, 4, 6, 8, 10. They have the same end behavior. It's top in, top out, or if they open down, it's bottom in, bottom out. And then x cubed, we know what x cubed looks like. It comes in the bottom and goes out the top. This quintic polynomial, which is another odd number, 5, comes in the bottom and goes out the top. So that's going to be a common characteristic among all odd degree polynomials. They have opposite end behaviors. If it comes in the bottom, it goes out the top. If it comes in the top, it goes out the bottom. Okay? All right. Here are the parent functions for all of the polynomials of this degree. Okay? We can call it x to the n. This is your parent function, x to the first. It's your linear parent function. Everyone knows what this one looks like, right? This is the one you're familiar with in Algebra 1. It has the domain of all real numbers, doesn't it? What's the range? All real numbers. Yeah, let's talk about that. The domain is all real numbers. The range is also all real numbers. And what do you know about the end behavior? Let's do the end behavior. The limit as x goes to negative infinity of y, and the limit as x goes to infinity of y. Let's copy that. I want to copy that so I can put the same information on all of these. All right, so what is the left end behavior? Negative infinity, and what's the right end behavior? Positive infinity. These are, I'm just going to put OPP for opposites. Or I'll write it out, opposite. They have opposite end behaviors, bottom in, top out. And that's degree 1. Degree 1. All right, what's your parent function for all quadratics? It's your y equals x squared, which is degree 2. Yes? What's the domain? I'm going to paste this. All All real numbers. What's the range? Anything greater than 0. What about 0 itself?
Yeah.
Yes, so I'll put 0 with a bracket to infinity. I'll do it in interval notation. Y epsilon, 0 inclusive, going to infinity. All right, what's the left end behavior? Infinity. What's the right end behavior? Infinity. This has the, not opposite, but the same end behavior. Yeah. Same end behavior. All right, your parent for all cubic functions, even the one that wiggled up here. Well, we haven't seen the one that wiggled. This is your parent function for all cubics. All degree polynomials of degree 3 are going to be cubic, and this is their parent function. And let's go ahead and paste our questions that we have. What's the domain? All real numbers. What's the range? All real numbers. Okay? Just like x to the first, which was another odd number, right? The domain and range were both all real numbers. Okay. What's the left end behavior? Negative infinity. What's the right end behavior? Infinity. They have opposite end behaviors. Just like the other odd function, x to the first over here, odd degree function. Oh, by the way, when I say odd degree function and odd function, does that mean the same thing? X to the third is an odd degree function because its exponent 3 is an odd number. If I say it's an odd function, that's talking about what type of symmetry? Y-axis or origin? Odd function is origin symmetric. Yeah. Does this function also have origin symmetry?
Yeah.
Yes, so it's also an odd function. You got to be careful when we say odd function, which is origin symmetric, and odd degree. This also happens to be an odd function, isn't it? It's an odd degree function, that's an odd function. All right, your quartic, this is your degree 4. It looks like a parabola, except it's flatter. Between -1 and 1, it's flatter, it's closer to the x-axis, and outside -1 and 1, it's steeper, okay? But this is what the fourth degree parent function looks like. What's its domain and range? Domain is what? All real numbers. What's its range? 0 inclusive to infinity, right? Yeah, 0 inclusive. Just like x squared, right? Just like x squared. It's an even degree polynomial. Is it also an even function? Even functions have what type of symmetry? Y-axis. So it's an even degree function because x to the fourth 4 is an even number. And it's also an even function because it has y-axis symmetry. All right. What about the left-end behavior? It's infinity, isn't it? And the right-end behavior is infinity, which is the same. They have the same end behavior. Just like x squared. Top in, top out. Top in, top out. Same end behavior. Yeah. All right, then your quintic. This is your parent function for your quintic. He looks a lot like what other parent function? He looks a lot like the cubic function, doesn't he? The only difference is, like the quartic is flatter between -1 and 1 and steeper outside -1 and 1. Same goes with the quintic. It's flatter between -1 and 1 than x cubed, and it's steeper outside -1 and 1. I think you can kind of see that here. So what would the domain be? All real numbers. What would the range be? All real numbers. What's the left end behavior? Negative infinity. And what's the right end behavior? Positive infinity. These are the opposite end behaviors, much like x cubed. So what I'm trying to get you to see here is based upon the degree of the polynomial, what the end behaviors look like, whether they're the same or they're the opposite. Right now, whether they're the same or the opposite, okay? And so we can summarize. If the end behaviors are the same, top in, top out, or later bottom in, bottom out, it should be a degree what? Even or odd? Even. Even degree polynomials like x squared, x to the fourth, and guess what? X to the 6. Guess what x to the 6 is going to look like?
Like a more flat version of x to the fourth.
It's going to look like a more flat version of x to the 4th. And x to the 8th is going to be a more flat version than x to the 6th. It gets harder and harder to draw it. Okay? But it's going to be steeper outside 1 and -1, 1, and less steep in between. Okay, what about the odd degrees? X to the 1st, x to the 3rd, x to the 5th. What do we know about their end behaviors?
They're opposite.
They're opposite end behaviors. Bottom in, top out, or later in, top in, bottom out, if you reflect them across the x-axis. Okay? They have opposite end behaviors, and they're all odd degree. 3, 1, 5. Okay? Or 5, 3, 1. Whew! So we can identify polynomials from their equations, And now we can identify polynomials from their graphs, can't we? No discontinuities, no cusps, sharp turns, or corners. And what do we know about the exponents on all the terms that have variables on them? They have to be what types of numbers? Whole numbers. And what's the domain of any polynomial? All real numbers. Okay. I think that's a good place to stop for today, really. We can get into sketching these transformations tomorrow. But I think I want you to digest what we have so far, because we learned a lot of technical stuff. Like this up here, this definition, this a sub n, x to the n, that's pretty technical. So I want to make sure that you have a chance to properly digest all today's information. All right, you can start with your worksheet if you want, or you can finish that Tetris game that's been bothering you. Just be productive. Any questions? All right, we got 5 minutes left to digest.